Right, so we're on to Zeno, the second of the Eleatics. Can't really say much about Zeno. He flourished around about the same time as Parmenides. He also lived in Elea, as we know. And by all accounts, it seemed that he was a student of Parmenides. Not a lot known about his life because none of his writings, his actual writings, survive in this case. And most of our information about his life comes from the work of later Greeks, but particularly from Plato. But he seems to have been a pupil and a possible lover of Parmenides. So in Plato's got a dialogue called the Parmenides. So focuses on Parmenides and Zeno coming to Athens, and they meet Socrates in this dialogue. We don't know whether they actually did meet, but it seems possible, very possible. And in that dialogue, at any rate, Zeno is about 25 years younger than Parmenides, and Plato talks about the fact that elsewhere he talks about the fact that when Zeno was a young man, Parmenides was particularly fond of him, and there's sort of overtones there that in fact, so very often in the Greek culture, an older male would take a younger male as a kind of companion and lover, and it was a common thing that they did. So it seems to be quite possible that Zeno was not only a pupil but a lover of Parmenides. Anyway, we're going to be interested in his arguments, and there he is. What a surprise! He's got a big beard. So moving to, we haven't got the writings that he got, but we've got reports of how he argued, and here's a particularly influential, I suppose, summary of the argument that Zeno gives. So he gave a number of different paradoxes, trying to argue that change, and in particular motion, is impossible. So this is, in line with the standard Eleatic idea that change and motion isn't possible, the Parmenidean idea. But Zeno's got a different way of trying to argue for this. But again, it involves the idea that if we do try to think that motion takes place, or we try to make sense of the notion of motion, that is, and what is motion, by the way, other than change of position over time? So motion is a type of change, it's a change in position. So here is the particularly well-known summary of the Zeno's argument, and it comes from a chap called Max Black, who was a philosopher. He was writing in the 1950s predominantly, although a bit before, a bit after as well. Here we go. Suppose Achilles runs 10 times as fast as the tortoise and gives him a 100-yard start. So I should say we're here looking at the most famous of the Zeno paradox, the Achilles and the tortoise. He's got some others. I mentioned one other in the book, the arrow paradox, but we won't be looking at that one. I'm just going to focus on this one to give us an idea. So suppose Achilles runs 10 times as fast as the tortoise and gives him a 100-yard start. In order to win the race, Achilles must first make up for his initial handicap by running 100 yards. But when he has done this, and he has reached the point where the tortoise started, the animal has had time to advance 10 yards. While Achilles runs these 10 yards, the tortoise gets 1 yard ahead. When Achilles has run this yard, the tortoise is 1/10 of a yard ahead, and so on without end. Achilles never catches the tortoise because the tortoise always holds the lead, however small. So that's the idea. I'm going to try and illustrate this on the board again. So let's open up my board. Here we go. Alright, so we've got a race between Achilles and the tortoise. We'll see this raises some interesting ideas. And this now is not a timeline, but a distance line. Suppose we've got, I might not put it in exactly the same terms. Suppose we've got a 100-meter race. Okay, 100 meters. So that's 100 meters. And then what we've got here, we've got Achilles at the front, the fast runner. Right, there he is, ready to go. And then we've got a tortoise. There's the tortoise. And what we're supposing is Achilles says, well, you're much slower than me, I'm going to give you a head start. So then we suppose that the tortoise sets off at a constant pace along this track. And we're to suppose that the tortoise gets a certain way ahead. Let's suppose he gets to the midpoint here, travelling at his slow pace. Well, I don't know, let's suppose he's moving at, what's a slow pace? 1 mile per hour or something, okay? So he reaches this point before Achilles sets off, okay? And we can suppose that Achilles, being a very fast runner, doesn't really matter what we set it at. Let's suppose he runs at, I don't know, what's a fast run? 25 miles per hour. Is that fast? I don't know. Anyway, it'll do. Clearly fast enough for him to catch up and overtake the tortoise before the tortoise reaches the finish line. But Zeno's idea here is, well, it doesn't matter how fast he's running because Achilles has got to cover this distance here, right, and reach the point where the tortoise currently is, right, in order to catch up with him. But by the time he's reached that point, the tortoise will have moved on a bit till, say, this point. So by the time Achilles reaches here, the tortoise will be here, i.e. still in front. So then what Achilles has got to do is to travel to this point here to catch up with the tortoise. But by the time he's travelled to there, the tortoise will have moved on a little bit further. So by the time Achilles reaches here, the tortoise is still in front. So what Achilles has then got to do is to reach the point where the tortoise now is. But by the time he reaches that point, the tortoise will have moved on a little bit more. So he still won't have caught him up, and he'll have to travel this distance to this point. But by that time, the tortoise will have moved on, and he's got to travel this distance by that time, and so on. And the point is, that iterates. It's going to go on. We can keep saying every time Achilles reaches the point where the tortoise is, the tortoise will have moved on a little bit more, right? So it looks as though Achilles can never catch up with the tortoise. So goes the original line of thought. So it's a paradox. We know very well that Achilles can and will catch up with him, but the problem is, well, what's going on? It seems to be a perfectly good argument, this, that every time he reaches where the tortoise is, the tortoise will have moved on a little bit. And we've got to notice here, I suppose, that these distances are obviously getting smaller and smaller and smaller, so that, you know, we get this, by the time we get up to here, and we're talking about, you know, I can't really draw it, if we zoom in on that, then we're going to have again the same kind of a pattern where this is getting smaller and smaller and smaller, right? And there Achilles is sort of catching up like this, but the tortoise is always ahead. And then we can zoom in on that, and it's going to be again the same pattern repeated. Oop, no, hang on, that's not right. The same pattern repeated. So if we zoom in on this bit here, then we're going to get smaller and smaller intervals. Oop, oh dear. Smaller and smaller intervals again, and da-da. Then we can zoom in on that. So it's going to be this constant zooming in, and we'll always find that there's a little bit, right, a little bit of a distance that the tortoise maintains ahead of Achilles. One way of thinking about this is to suppose that, well, does that, I mean, if we suppose that space is infinitely divisible, so really the key thing to think about here is the notion of the divisibility of space and of time, by the way, because we're not only dividing up space, we're going to have the time that it not only that it travels shorter and shorter distances here, but the time he takes the tortoise takes to travel those distances is going to be a smaller and smaller amount of time as well. So we're dividing up both space and time into smaller and smaller and smaller and smaller chunks. And if that process really can go on forever, that we can continually divide up space and time into smaller and smaller chunks, then one way of thinking about the problem here is in terms of tasks for Achilles. So Achilles, we can put it like this: in order to catch the tortoise, first has to complete the task, call this task 1, of catching up to where the tortoise is. By that time the tortoise has moved on, so then he's got to complete task 2 to catch up where the tortoise is then. So he's got to complete task 3 and task 4 and da-da-da-da-dum. And if we can keep going down and down and down and down and down, these tasks never end. So although the distances and the time are getting shorter and shorter and shorter, it's still an identifiable task. And the idea here is meant to be Achilles is going to have to perform an infinite number of tasks in order to catch up with Achilles. With the tortoise. And that means movement, any movement, so this, to catch up with the tortoise in this case, requires Achilles to perform an infinite number of tasks in a finite amount of time, right? And the question is is that possible? Is it possible to perform an infinite number of tasks? Alright, I'm not really going to say too much more about this. We can talk about it in the seminar if you like. Many people think that modern mathematics has solved this problem. Many people think, well, yeah, it is possible to perform an infinite number of tasks in a finite amount of time. But it's not clear to me that the mathematics has really solved this puzzle. It does seem odd. I mean, just so you know, one solution to this is to say, well, actually, we can't keep dividing up time and space in this way. In fact, what we've got to think rather is that time and space come in like discrete chunks. I don't know, we draw them like that. And movement really involves sort of jumping across these discrete chunks. So at some point along this way, the idea is meant to be here, when Achilles reaches where the tortoise is, the tortoise won't yet have moved the next chunk of space on. If you can't divide space up into infinitely small slices, then it's not going to be the case that the tortoise will have moved on. It'll still be stuck at the same chunk that Achilles has reached, something like that. So one solution to this problem is to think that we can't keep dividing up space. There are some smallest distances that are possible, and by the same line of thought, the smallest amounts of time possible. But that's controversial, and it doesn't seem to be the way in which, for example, modern physicists think about space. They do think about it as being infinitely divisible. And maybe I'll say just a couple more words. We'll come back to these ideas later. So yeah, one other thing I will say here is that all of this stuff that I'm talking about here in these introductory, in the first few weeks, the historical background, it's just meant to get your sort of mind working. We just get you thinking about some of these ideas. We're going to come back to them later and try and assess them. At the moment, I'm raising these ideas, getting you to think about them. But I will mention this. The notion of infinity, to do with both time and to do with space, is a very, very interesting notion, and we're going to have to say more about infinity in due course. But I will say this: it turns out that there are more than one level of infinity. So infinities come in different sizes. That might sound very odd. I'll try and explain in due course exactly how and why that is so. But the type of infinity that we're currently thinking about is the infinity to do with the rational numbers. So we'll talk a bit about this. It's not going to be absolutely crucial that you follow it, but it is an interesting thought. So, okay, let's put it like this. If we just put the counting numbers 1, 2, 3, 4, 5, the integers in other words, 6, 7, 8, or sometimes they're called the natural numbers. Mathematicians call these the natural numbers. These go on for infinity, right? They never end. Every time you get any number, no matter how big, you can always add one more. All right. And there, notice that there is no number called infinity. It's not like if you count for long enough, you hit one number that's called infinity. So to say that there are infinitely many numbers, it's not true to say that any of those numbers is the number infinity. There's no such number as infinity. It's rather there are infinitely many numbers, first thing to say. And then suppose that we've got some spatial, or this could be a temporal line, it doesn't matter, some line or other that we divide up in terms of the integers. Those are meant to be evenly spaced. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Notice that we can split up the line even further. We can go to a half in here, 1.5 in there, and so on. And then we can split that up into a quarter, an eighth, blah, blah, blah. And here the idea is we keep going down and down and down and down and down. Well, here's a very interesting thought for you, and we'll come back to this kind of idea. Suppose we take the interval between 1 and 2 then. Oh, I've put a half in there. Sorry, that's meant to be over there, obviously. and 1.5 is there. Anyway, you get the idea. So let's take the interval between 0 and 1, a line segment, and let's take a point upon the line. Let's take half. So this is the point midway between 0 and 1. And if we think about that as a point on the line, and I ask you, well, what's the next point on the line? What's the point that immediately follows the point that's at a point, the halfway point? How do you answer that question? What is the next point on the line? Is there a next point on the line? Well, suppose you say, well, it's just a little bit more than a half. Well, okay, let's suppose, so if we've got a half, what would be a little bit more than a half? Well, let's take the point which is, I don't know, 501 over 1,000. There we are. That's a little bit more than a half. But the point is, well, there's a point between a half and 501 over 1,000. For example, there's the point which is 5,001 over 10,000, right? And then you could have 50,001 over 100,000 is between them. And you can always find another point which is between the two. And I guess that's kind of, if you divide down any line far enough, you take any 2 points on this line, there's always going to be a point in the between. And if we take that point, there's going to be a point in between. So this is a consequence of the idea that you can constantly divide up things down. A way of putting it is, if you take a point on a line, there is no next point. There's no such thing as the point that immediately follows it, if the line is infinitely divisible. And that's going to apply both to spatial lines and temporal lines, if we think about temporal lines in that way. So yeah, one consequence of this, and this is the reason I mention this now, is it feeds into the Zeno paradox, because it looks like, movement involves moving from one point to the next point. But in fact, if there is no next point, then it makes movement seem somewhat mysterious. How do you move from one place to another if there's no next point for you to move into? I mean, all of this is rather vague at the moment, but I hope you see that there are some interesting issues to do with infinity here, which we can kind of draw from the Zeno paradoxes when we start thinking about them. Alright, so the next video then, we're going to move to Plato. I might do Plato and Aristotle in one video, although they're big names in philosophy. I'm going to cover them quite briefly because, well, Plato did in fact have that much of interest to say about the philosophy of time. He had a little bit, as I mentioned before. It's really what I want to draw from him is this idea of the two types of eternity. I'll say more about it. And Aristotle, I'm not going to spend too much time on his view because it was utterly confusing, although there are some things which I'll mention. We've got to mention Plato and Aristotle because they were such big names and because they did say something about time. But we're not going to dwell on their views. Okay, so let's move to their views then.